Hi, I'm Mark Howenstein with Technical Designs. As the mechanical engineering firm for the Fernley Intermediate School, I want to share with you the mechanical design overview and review the design concepts and system components. This school design incorporates some of the latest ideas in ventilation, renewable energy, and facility control strategies. To understand the mechanical systems, we will present the following ideas: system overview and system components, water source heat pump concepts, how solar is incorporated into the design, and finally, building control strategies. A little disclaimer here, this presentation draws from a lot of different sources, including the manufacturers that have supplied the equipment, so copyright protection, use with permission, etc., etc., etc. The mechanical system is designed around roof-mounted water source heat pumps, boilers to add heat to the system, a cooling tower to remove heat from the system, pumps to circulate the water around to the 46 roof-mounted units that provide heating and cooling to the individual classrooms and occupied spaces throughout the facility. The heart of the mechanical system design is the roof-mounted water source heat pump. We will talk a little more about the heat pump and how a heat pump operates, but for now we will look inside the units on the roof that provide individual zone control for each classroom and occupied space. The packaged units provide heating and cooling depending on what the space thermostat is calling for. The basic components of the unit are item 2, the compressor, item 4, the DX coil, item 6, the fan, and just behind the compressor is a heat exchanger that transfers heat from the water circuit to the DX circuit. Item 7 is the air side economizer. The role of the air side economizer is to cool the building using outside air rather than running the compressor. This provides two benefits. One, cooling the space without using the compressor energy, and two, using as much outside air to ventilate the space as possible. We'll come back to the water source heat pump, but for now let's look at the other parts of the system. The mechanical room in the north part of Area 500 in the building houses the boilers, pumps, and cooling tower. The boilers are designed to heat both the condenser water loop and the hydronic heating loop. The hydronic heating loop goes out into the building and with heat exchangers in the bottom of each domestic water storage tank heats the domestic hot water. The system rejects its heat at the cooling tower. This school uses a closed circuit tower. This just means that the unit is like a large air handler with a finned coil. The condenser water is inside the tubes of the coil and the water is evaporated on the fins of the coil. This provides maximum cooling while isolating the condenser water loop that's propylene glycol. The tower has controls to maintain the condenser water loop temperature. During the winter, the condenser loop bypasses the tower altogether, and as more and more cooling occurs in the building, the water is circulated out to the tower coil until the tower basin pump starts to circulate water over the coil and fin. The fans are staged with variable speed drives. Note that at Fernley, the basin of our tower is a large water storage tank underground. This does double duty depending on the time of year. So now that we've toured the building, let's look at the water source heat pump and how it operates. A heat pump is basically a device that transfers heat from one substance to another. A heat pump has these refrigerant components: a compressor, condenser, evaporator, and expansion device. A heat pump is different from standard refrigeration equipment because it can reverse the refrigeration cycle to perform heating by reversing the function of the two heat exchangers. The operation of the refrigerant cycle changes depending on whether the unit is in the heating or cooling mode. So a heat pump is basically a device that transfers heat from one substance to another, and a heat pump that transfers heat from air to water and vice versa is called a water source heat pump. Advantages of the water source heat pump are individual space control, performs both heating and cooling, standard DX training to maintain units, flexible to operate one or two units without a full central plant operation, redundancy, and heat recovery, which we will cover next. Now that we've looked at the individual unit operation as a heat pump, let's look at the system. Water source heat pumps can run either in heating or cooling mode when the water loop temperature is maintained between 60 and 80 degrees. During warm weather, when all the heat pumps are operating in cooling mode, heat removed from the air is transferred to the water loop. This causes the temperature in the water in the loop to rise, making it necessary to remove heat from the water. A cooling tower or evaporative water cooler rejects this heat to the outdoor air, maintaining a leaving water temperature of approximately 90 degrees. Remember now that the unit's first stage of cooling is outdoor air, so when the outdoor air temperature is below 60 degrees, the units will cool without running the compressors. During cold weather, when most of the heat pumps are operating in heating mode, heat is removed from the water loop and transferred to the air. This causes the temperature of the water in the loop to drop, making it necessary to add heat to the water loop. The boilers add heat to the loop, maintaining a leaving water temperature of approximately 60 degrees Fahrenheit. During mild weather, such as spring and fall, the heat pumps serving the sunny side and interior of the building operate in cooling mode and reject heat into the water loop. The heat pumps serving the shady side of the building operate in the heating mode and absorb heat from the loop. Heat rejected by the units operating in cooling mode can be used to offset the heat absorbed by the units in the heating mode. If the water temperature stays between 60 and 90 degrees, neither the boiler nor the cooling tower need to operate. In this manner, a water source heat pump provides a form of heat recovery and an opportunity to save energy. This is the heat recovery concept used in heat gathered from one part of the facility and using the heat in another. Heat generated by lights, people, and equipment may require year-round cooling in the interior spaces of a building. In these applications, the benefit of the heat recovery further reduces boiler operation during the winter months. Okay, so we see how water source heat pumps are sharing the heating and cooling. Two other energy strategies were used as well on this project: heat recovery from the classrooms and solar hydronic heating. Suppose your building is in the heating mode. The roof-mounted solar panels collect heat and store it in our tower basin tank in the winter. The loop captures as much heat as possible and heats the glycol condenser loop with the help of a plate and frame heat exchanger mounted in the mechanical room. This approach works great in the winter months, but to take advantage of the heat that the panels create in the summer, we divert the solar heated water to the hydronic heating loop. This then transfers heat into the building to heat the domestic hot water. As a result, the solar panels provide two different heating functions depending on the time of year. Another aspect of heat recovery is using the airside economizers. In each of the classrooms is a CO2 sensor. The function of the sensor is to make sure each classroom is receiving enough ventilation air. Because of the occupancy, classrooms require a lot of outdoor air. Conditioning this air is an expensive proposition, and most times it's just exhausted out of the building. In the classroom wings, we use this conditioned air to heat and cool the hallways. Transfer grills in selected lockers move the air between the classroom and hallway, eliminating the need for additional hallway cooling units. Effective building and space pressurization control not only ensures proper distribution of conditioned and ventilation air to the space, but also can confine odors and contaminants to specific areas of the building. We've covered the thermostats and the CO2 sensors in the space, but we have yet to discuss the overall building control system. The Fernley School has a complete BACnet-based integrated control system. Each unit operates in a standalone fashion, but communicates to the web-based front end what each unit is doing and if it's in trouble. There will be more detail on the building control system, but for now, let's look at just one or two energy saving features that occur when you have all things talking to each other. In many buildings, the temperature set point of the space thermostat is set back during unoccupied hours in the winter. For example, the space temperature is controlled to 68 degrees during the day, but allowed to decrease to 60 degrees overnight. This practice is called night setback. While it saves energy during unoccupied periods, night setback imposes an additional heating load on the system when the set point is reset back to 68 degrees. This is called morning warm-up. Because all heat pumps could start simultaneously when the set point is reset, the boiler must have sufficient capacity to provide heat to all the heat pumps. This could cause the boiler to have larger capacity than needed during normal system operation. One way to reduce the required boiler capacity is to stage units on in an organized fashion. When night setback is used, the boiler is operated to increase the temperature of the water in the loop and to ensure that the morning warm-up can be satisfied. Staggering the start of the heat pumps during morning warm-up using a system-level controller can eliminate the need for a larger boiler plant. We can also allow our domestic hot water set point to drift during unoccupied hours and then stage bringing the system back to set point at a time that doesn't conflict with the building heating demand. Technical Designs would like to thank J.W. McClenahan and Gardner Engineering for their skill and efforts as the mechanical and plumbing contractors. Their hard work has taken the latest concepts and turned them into reality.